linearization of a function denoted by
L of x.
very good, L of x indeed, is a blah 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 function that blah 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 the value of the function near x equals a. The linearization of a function is a function that the value of the function f of x near x equals a.
Linear.
Thank you.
Approximate.
Yes, that approximates. Very good. The value of the function, or approximates if you want the function, but it's the same thing. Using the instead of the actual function, there will always be this gives away the word here.
Error.
Yes. So using the
Linearization.
very good. Always. That's always the case because I'm not using the function, I'm using the tangent. I'm using the equation of this tangent instead of the function. So I will always have an error. It's an approximation. Awesome. That's what we say here. It's not the same. Good. Any questions from me? I extended this homework that was due today. I extended it to April the 3rd. So you can work on it again. You can submit it again. It's up to you. But I will add some more homework, another homework actually, for April the 3rd. Okay? Any questions? You need any help with anything, my lab math or anything, any problems? Before we continue with differentials. So let me refresh your memory. We said that L of x equals f of a plus f prime of a times x minus a. I want to put it here because I want you to see that what we are going to look at is extremely similar to this in a moment. And of course, near x equals a. So the linearization can be used to approximate the function near x equals a. Okay, so now let's continue with differentials. It may look weird, but if you stay with me, you'll see it's exactly the same in a minute. Different notation. Okay, so we have our best friend, f of x. And we said we have a point here, x, and of course f of x. And we have a point extremely close to this one, but I'm zooming in. So now it looks here, but it's extremely close. And it's very close, and because it's very close, we're going to denote this by delta x or dx. I will write again what they represent in a minute. So then this is x plus delta x or x plus dx. They're all the same. These two are the same. And this point is the same with x plus delta x, and the same with x plus dx. Last time you already told me that this must be f of this point. So two different ways to write it. F of x plus delta x or f of x plus dx. They are the same. And with your permission, I'm going to write here what they represent and graph it again because I need it again on this paper. So delta x actual, if you want to call it error, it's called, you can call it error or actual difference, or error or a minor tolerance, sometimes it's called. So actual error in x. Instead of being here, we're a little bit to the side, or here or this side. It doesn't matter, but I'm zooming in and it looks huge. No, it's very, very close. So the actual error in x dx is, although it's the same measure, it's not called the actual error. It's called the differential. Differential of x. So why do we use two different notations? Why isn't this the same thing? Why do we have to use delta x and we use dx? Well, delta x will go with the actual value and dx will go with the approximate value. So, and dx also involves the derivative. Is connected to f prime. This is f and this is f prime. So that's why it's dx and not delta x. It happens that they are equal in measure. But dx has something to do with the derivative. Delta x is all algebra. Plug it in. So if you want, it's algebra. Has nothing to do with calculus. Okay. Now, from this picture, although I'm going to graph it again, from this picture we know that this is what is called delta y. Delta y, again, is algebra. It doesn't have d. It has delta. Okay, so what is delta y? Actual error in y, or in other words, in f of x, triggered by the error in x. So if I have an error in x of dx or delta x, we create an error in the y value. Instead of being here at f of x, it's up here at f of x plus dx or f of x plus delta x. So this change, if you want, or error, this change in x created this change in y values instead of being here. Okay, and what is the formula for delta y? Delta y is f of x plus delta x minus f of x, which is this distance. This minus this is delta y. Okay, one more step, but I'm not going to go back there. I'm going to graph it again. Bear with me. I'm going to put everything again in the same spots. Good. We already have this. We already have this. And now, of course, we are talking about calculus. So at this point, because this is what we're interested in, it happens that there is an error that triggers this error. Of course, I'm going to draw our second best friend, the tangent line. At this point, I am going to extend this vertical line, and I already have this horizontal line, and I'm looking now at this triangle. So this is the triangle that we are going to discuss for a moment, and then you'll see what happens. Okay, I know this piece. I know the slope of this line. Can anyone again We used this last time in finding the equation of the tangent line. What is the slope of this line? Anyone? Thank you very much. It is f prime of x. And now, looking at this triangle for a second, I know that the slope of this line is f prime of x. But is there another way with algebra? Is there another way, not calculus, is there another way of determining the slope of this line with algebra now? What is the definition of the slope? Anyone remembers?
Is it y2 minus y1 and x2 minus x1?
Excellent, brilliant. Rise over run. Can anyone give us, so I have the slope, which is f prime of x, which is rise over run. Let's start with the run. What is the run?
Is it dx?
Of course, awesome. So now the question is, what is the rise?
Is it delta y?
Careful. This is delta y. This is the exact, the actual, exact. So this is the question. You can say, but these are very close because this point is here. I agree, but it's not exactly the same. So the actual error is this. What could this be? Don't say anything. Let me give you a hint. We've seen this so many times. What could this be?
Y?
Say it again.
Is it dy?
Thank you very much. So this is dy. Now the question is, what is dy? We know what delta y is. We know what f prime is. We know what dx and delta x. All of a sudden, there is a dy now. Okay. dy, what do you think? Is the name
Is it the y?
the differential of y? Of course. Differential. In other words, is this actual error approximated and determined with a derivative?
Yes.
Differential of y. Now, can anyone solve this equation and give us dy? I have,
It's f.
yes?
It's f prime times dx.
F prime of x dx. That's it. So dy equals f prime of x dx. Final step. I promise. This is it. Final step. So delta y is the exact error. dy is the approximation. What symbol would you put in between these two? What symbols we have? Greater than or equal to, greater than, less than or equal to, less than, equal symbol, and approximate. From
Approximate?
these, of course. Of course. How come? You can say, look at how big this is and look how small this is. No, no, no. Remember, this point is right here. I zoomed in. So these are very close to each other. The actual error triggered by delta x is very close to the error we approximate using the tangent. So this I'll replace with f of x plus dx minus f of x, because that's what equals to. This, can anyone tell us again what dy represents?
F prime of x times dx.
I'm going to move this to the other side. And Let's take a look.
That's the same thing.
Exactly. So this is the approximation. Here it's the equal symbol because we named this L of x. But this is what we are looking at in the approximation. This is the f of x or f of a. This is f prime of a or f prime of x. And this is the minor difference in x, dx. So it's exactly the same thing. Now, what do we do with this? What is this all about? Okay, so let's see how we apply this. And I'm going to share my screen. And I thought I had the book here. No, I guess I didn't. And this will be the end of